So thank you very much. So many people have mentioned the broadness of Maxim research. And in this respect, I remember one conversation with Dennis Sullivan. Actually, it's related to Jean-Pierre's introductory words, when they were thinking whom they should hire at IHS. So, and years ago, years after that, I saw Dennis at the Simon Center and spoke to him, and he said, well, at the time there was a manuscript never published by Maxim, sort of a Dune program about the Chern-Simons, Vassiliev invariants, many other things. And then he said, well, I looked at it, and that guy wanted to achieve what I wanted in topology and even more. So then, and they just a topology. So some theories invented by Maxim, they were developed by other people. This concerns Motivic integration, which is related to my talk. And when preparing the slides, I thought about some visual image, some picture, which on one hand demonstrate Maxim broadness, and on the other hand is somehow related to the subject of my talk. So that's a photo. It's taken like, I believe maybe 16 or whatever, many years ago. Maxim was interviewed for a newspaper, and that photograph was taken at the time. And the idea was to put some of his achievements on the photo. And if you look, you can see indeed some of them. For example, you can see his formula for the number of point curves on P2 of passing through the given number of curves on P2 passing through the given number of points, which is, of course, Gromov-Witten theory. You can see some formulas related to deformation quantization, actually to Deligne's conjecture, if you look carefully. And there is a fragment here, which is a wall-crossing formula, which is, of course, a part of our Motivic Donaldson-Thomas theory. And a more advanced formula, this is just a simplest case of rank 2. More advanced is on my t-shirt, so after my talk you can come and see, or just read or just read our paper. All right, so then the broadness is demonstrated, and the relation to my talk is a Motivic Donaldson-Thomas theory. So what is my talk about? It's a joint project with Roma Fedorov and my son Alex Soibelman. It's based on our 3 papers, which are in the archive, and the last one is quite recent. Probably very few people saw it. So in those papers we computed Motivic Donaldson-Thomas invariants for the moduli stacks of, in general, irregular semistable parabolic Higgs bundles. The group GLN is always for my talk, or for bundles with irregular connections. We do it for the curves, well, geometrically connected projective curves, but over characteristic arbitrary field of characteristic 0, so the transcendental methods like harmonic matrix and so on are not available. All right, now, and here the notion of Motivic Donaldson-Thomas invariant, the quantity which we will compute, which we have computed, was introduced for the first time in our paper with Maxim in 2008, together with these wall-crossing formulas which I mentioned. All right, so moduli stacks of what? Very briefly, for those who have never seen. So Higgs bundles for us will be pairs of a vector bundle on the curve and a morphism from the vector bundle to its tensor product with a line bundle. So if the line bundle is a canonical line bundle, then it's standard definition for algebraic geometers of the Higgs bundle. But we will need to consider singulars, so we will consider a divisor, effective divisor, and as a line bundle it will be a twisted canonical bundle. So we will do parabolic Higgs bundles and parabolic connections, which mean that to the points on the support of the divisor, you see multiplicities, they are not necessarily reduced, our divisors. So to the point we assign flags. In the regular singular case, when all the multiplicities are equal to 1, which means that the Higgs field or the connection has pole of degree 1 at most, we will consider arbitrary flags of vector spaces. For irregular, which is the most interesting and new as of today part of our project, we consider only full flags. But these are not full flags of vector spaces, they will be free modules over truncated local ring, or algebras of truncated polynomials. So, and for connection, the story is similar. We combine both stories in one and consider epsilon connection or whatever. There is no good name for this. You know, Delin call it lambda connection. Some people call H-bar connection. So whatever letter you use, for me today it will be epsilon connections. So the quantities like this, which satisfy the Leibniz rule. So when epsilon equal to 0, we get just Higgs field. Otherwise, it will be a connection.
Is it possible to ask, so in the irregular case, are you putting in a compatibility condition between the...
Yes, of course.
You didn't write it there, you just wrote it for the tame case.
What? No, you will see. I will give precise definition, Phil. You know, it's first part according to, it should be elementary with skipping many details. But at some point I will be very precise, which will make you probably happy, but the rest of the audience not.
Complex symplectic spaces, I mean, that's my basic question.
You have to fix something if you want to get symplectic, but I'm not doing that. So the stacks will be twisted cotangent bundles in the end, so in some sense they will be symplectic. All right, anyway, what kind of quantities we compute? So they can be called Motivic volumes because they are integrals in some sense, or the stack of objects. And we will either fix a Chern classes, like considering bundles with fixed rank and degree. Questions? No? Great. So we will consider, for example, bundles with connections of fixed rank and degree, and we will consider also generating functions over this lattice of all Chern classes, or more typically, since the rank is non-negative, it will be a submonoid in this lattice. So this generating function live in the Motivic Hall algebras, which I recall briefly later, and also in the Motivic quantum tori of the corresponding categories, like the category of Higgs bundles. So both algebras, Motivic Hall algebras and Motivic quantum tori, they are associative algebra of the ring of Motivic functions. And although it's kind of a pretty standard stuff, so in the elementary part of my talk, I will recall some basic facts about Motivic functions. So first, like Motivic measure, it's a sort of a generalization, universal generalization of the map, which is assigned to an algebraic variety, the number of points or a finite field. So it satisfies this assignment, satisfies the standard properties of the measure. And now in Motivic integration, people consider the universal ring, sometimes called K0 of varieties, such that such thing will be a homomorphism from the universal commutative ring to a particular commutative ring, integer numbers in this case. So this K0 of varieties definition is here. So it's generated by isomorphism classes of varieties subject to the Caesar relations. It has a commutative structure, it has a unit. And there are many versions of this. This is the simplest example of a Motivic ring, so I will call all possible versions which will appear in my talk Motivic rings. There is a version in which the Motivic class of a vector bundle is a product of the Motivic classes of the base and the fiber. So, okay, this is K0 of varieties. These are examples of realizations. Besides of the number of points, you can take the Euler characteristic with a compact support. If you are over complex numbers, you can take the Hodge polynomial. On the computational sides, if you can decompose your variety into the union of cells, or if you can represent it as a fiber bundle over something like vector bundle over the base, the Motivic class of which you know, you can compute the result. For example, for P1, yeah, it's like a affine space plus 1 point. And this L, Lefschetz motive, it plays an exceptional role in the theory, so it has a special notation. So this is trivial, affine line plus point. This is a little bit less trivial, but again, it's an exercise. And if you apply a realization, like the number of points, you indeed get some known formulas for the number of points of GLN or a finite field. So that's a thing. Now, I will consider stacks, like vector bundles. They have automorphism, so there is a generalization of that story. In the simplest case of algebraic variety acting by GLN, this is a definition. Actually, even here, in order to divide, you should do something, because you should introduce the inverse to the Lefschetz motive, and then this thing has a meaning as a series. Yeah, for nice enough stacks, algebraic stacks, like with affine stabilizers, you can stratify them into the union, in general, infinite, because I will consider in stacks, in Artin stacks, like this, and define the Motivic class in this way. But of course, you should be careful for the right-hand side to be convergent in certain sense. So from physics perspective, it's kind of a regularization procedure for the infinite sum. And also, symmetric functions will play a role, quite important, in my story, at least at the level of answers. And for that, I need a certain quotient of whatever Motivic rings probably people have seen, a quotient which is a lambda ring. Not a pre-lambda ring in the sense of Grothendieck, but a lambda ring. But again, to avoid these technicalities, I will denote by mod k, Motivic functions over k, an appropriate version of the ring of Motivic functions, so it will be always commutative unital, but which is a lambda ring. And when we have the lambda ring, we can apply symmetric functions for the elements. We have this plétistic calculus with plétistic exponent, inverse plétistic logarithm, like Adams operations. We have many nice things. And the last thing, which probably I will not need seriously, is a relative version when we replace a spec of the field by a more general stack. And there is a relative version of this. All right, I believe this is it. And two examples which illustrate that something can be computed in the ring of Motivic functions. This is, I believe, like 17 years old result of Berendt and Dillon. They computed the Motivic class of the stack of vector bundles on the same x is a smooth projective curve, R is a rank, D is a degree, and the answer is very nice. You see it's a closed answer in terms of the Motivic class of the Jacobian, and the product of shifted Motivic zeta functions introduced by Kapranov long ago. This is a definition. This zeta function, they will appear several times in my talk. So, of course, for the number of points of the finite field, it's a kind of analog of the Ziegel's formula. So this is something in dimension 1. And this is something in dimension 2. It's a Götzsche, Motivic version of Götzsche formula. So S is a smooth surface, or algebraically closed field of characteristic 0. And this is a generating function of Motivic classes of Hilbert schemes. So it's again something additive is equal to the product. So and we will see more examples of this sort. So it's, if you'd like, you can think of this as a version of Euler formula. So you have something additive on the left-hand side and the product on the right-hand side. But here zeta functions appear on the right-hand side. Anyway, these are just for illustration purposes. They will not play any role in my talk. All right, now here is, in case if I will be short of time, this is the summary of our approach, maybe for a few experts. We consider parabolic irregular epsilon connections for an arbitrary divisor. So, first kind of idea is to reduce the irregular parabolic case to the regular one. It's a non-trivial, of course, because for the regular we have just poles of degree 1. But there is, we invented some kind of inductive procedure which allows us to control how the Motivic class of the stack changes when we remove when we reduce the multiplicity of the divisor by 1. So this is the most technical step, which contains several non-trivial ideas. Now, when we are reduced to the regular singular case, this is an interesting story by itself. It's our 2019 paper. For example, for computations of regular singular, of the stack of regular singular Higgs bundles. So this computation we reduce to the case of nilpotent parabolic pairs, which means it's sort of a reduction to the nilpotent cone, if you'd like. Nilpotent parabolic pair, it's a pair, a vector bundle, and the nilpotent endomorphism. And in this case, there was a remarkable result of Melit, in the case of finite fields, and we found the Motivic upgrade, which says that for nilpotent parabolic pairs, the result is a product of the one with no marked points and no flags, and certain local factors. And these local factors, they're independent on anything. They basically depend, if you like, on the formal neighborhood of a marked point on the curve. So these local factors, they can be computed in different ways, and there is a nice, well, conjectural relation of this local answer to the geometric Satake for double affine Grassmannians and some work of Braverman, Kazhdan, and Patnaik on p-adic Hecke algebras. All right. Now, so then from the bird's perspective, it's kind of reduce irregular to regular singulars, then to nilpotent pairs, and this already gives some answers in terms of the shifted Motivic zeta function, like in the Behrend-Dillon formula, if you'd like, but more complicated. And then it can be simplified. And the point is that those answers, they live in some universal lambda ring, which I denote Kg, and which depend only on the genus of G and not on the global structure of the curve. So in this universal lambda ring, we simplify the answer and represent it in terms of some standard symmetric functions. And finally, we prove that there is a morphism of lambda ring from this universal lambda ring, where the answers are simplified, to the ring of Motivic function. This will give a very explicit formulas, which I will show you later.
Do you understand there is some kind of symbol for this universal ring corresponding to Jacobian curve, stuff like this? Because homomorphism should depend on the curve.
No. The homomorphism will depend on this data, but not the universal.
That's just not homomorphism. This element will go.
Yeah. Okay. Now another elementary part of my talk. It's a reminder. Now it's a part of the. I mean, all people who did something with Motivic Donaldson-Thomas invariant, they know it by heart, but for other, I will recall briefly our formalism, the categorical framework, which we need for the computations, categorical framework from our 2008 paper, which is remarkable by different reasons, and one reason is that it has never been published. It's only exists in the archive form. All right, so what is the setup? So we have a k-linear category with some additional properties, which let me call it int artin. In particular, the stack of object is a union over let me call this lattice of Chern classes of artin stacks. Like, for example, you can consider the category of, I don't know, coherent sheaves on the curve. So then gamma is generated by rank and degree by this pair, so it's z square as a lattice. Inside sits a monoid corresponding to true objects. So this is a starting point. Now, with this data, we associate what we call Motivic Hall algebra. It's an algebra of the ring of Motivic functions. And it's generated by constructible families of objects over over the stack of objects of my category. In particular, it contains delta functions corresponding just isomorphism classes of objects. And the associative product on this algebra HC, it comes in the standard way, like in any whole algebra or whatever. It comes from the stack of exact triangles, or we did it in a triangular framework, but you can do it in the abelian. So you consider then exact short sequences. So you have 3 projections to the 3 terms, and you do the pull back, push forward construction, which gives you structure constants of some associative algebra, which is known as a Motivic whole algebra. Good. First thing, now, if the category carries a Bridgeland stability structure with the central charge Z, then fixing a strict sector, a sector which is less than 180 degrees, we can define the category, subcategory, generated by semistables for which the central charge sits in this V. And so for such a category, we can define its Motivic volume as an element of the completed Motivic whole algebra. It can be schematically written like this. At least in this way, it's understandable what we do. We count every isomorphism class with a weight which is 1 or the motive of the automorphism group. So the reason why this V is chosen, because this sum, we sum over a cone, so this sum makes sense. So in the completion. And since we fix a stability structure, so we have a Harder-Narasimhan property. Every object admits a filtration with semi-stable quotients. And this implies that in this, actually in the completed Motivic whole algebra, we have a factorization, also known as a wall-crossing formula. So in the left-hand side, we have this, if you'd like, full Motivic volume of the stack. And in the right-hand side, we have a product of similar things. We just, instead of, we take a sector which is just array. So if you have, a sector V, so there are infinitely many arrays. So we take a clockwise product of Motivic volumes of categories corresponding to individual slopes, and these are they correspond to subcategories generated by semistables with a fixed slope, which belong to fixed central charge, which belongs to array. All right. Now, we proved in this 2008 paper that if C is a 3-dimensional Calabi-Yau category, then there is a homomorphism from the Motivic whole algebra, which is difficult to compute, to a simpler algebra, which is a quantum torus over this commutative ring. So this is a definition. It's a standard quantum torus notation. Here it's a motive of the affine line. So as I said, we should do something, modify. For example, we should add square root of L. But as I said, all versions of the ring of Motivic functions will be denoted by mod K. So that's a Motivic quantum torus, and there is this homomorphism. Now, the pairing is a skew-symmetrized Euler form. Well, for 3 Calabi-Yau, it's just skew-symmetric from the very beginning.
Do you need some orientation data?
We need many things. So, Tom, you want me to give a lecture course?
No, but you would ask me that question.
Yeah. All right, all right. So then I will remember. I will ask you something. Yeah. We need orientation data for that. Correct. Now, if we apply this homomorphism to the factorization formula in the Motivic whole algebra, then we get a factorization formula or crossing formula in the quantum torus. So we call the left-hand side Motivic Donaldson-Thomas series of this category. Now, if we take, for example, V to be a ray, it often happens that the corresponding Motivic whole algebra is just a symmetric algebra. Generically, this is the case. And then we can define the Motivic Donaldson-Thomas invariant using the plethistic exponent by this formula. So it's not, the nice thing is that this omega of gammas are kind of, at least in the limit when square root L goes to 1 or minus 1, I don't remember, 1 probably. These numbers become integers, so that's a good thing. In general, there are some Motivic classes, elements of mod K. And morally, these elements omega of gamma should be thought of Motivic classes of moduli stacks of semistables of the given slope L and of the given Chern class gamma. Like if you want to compute Motivic class of, I don't know, like moduli of semistable vector bundles, so that's omega of gamma, what you get in the end. Okay. So it's a difficult formalism, and so this is an illustration. So, Don, you are on the picture. Yeah, it's a historic photo, Arbeistagnum 2007, boat trip, Maxim and me explaining you our formalism. So,
so by now I should understand.
yes. Yeah, I mean, there is no audio, it's just photos, but anyway. So we were much younger, but it's not visible.
One doesn't look very happy on that picture.
Yes, probably the explanation was very understandable. I'm not sure about my today's. All right, so that's end of the Motivic part of the story.
So, is it possible to ask the, is it understood the relation to Stokes data that you've got these products of these things? Is it a categorified version of Stokes automorphisms, or is it still mysterious, or it's obvious?
Okay, in the general formalism, it's more or less as general as in Misha-Stokes. So it just this AL, whatever, which appeared in Kapranov stock, it's just automorphism corresponding to the Salian derivatives, if you'd like. In general, they are not computed. I mean, this is a problem, a mathematical problem, how to compute omega of gamma, and actually physics.
Is there an actual non-linear connection for which this is the Stokes data of it?
Yeah. Yeah, yes.
What was the answer?
The answer is yes. Yeah, but my answer coincides with the answer of my.
So what is the thing that it is the Stokes data of?
What is the thing? That's a different. Let me return to it in the end of my talk, because maybe you want to see the formulas for something in which Stokes data will be really Stokes data.
Is there an Ehresmann connection of which this is the Stokes?
Yes, it's a non-linear. It's a certain non-linear connection. You are right, but an infinite run.
Physicists. In some cases, omega of gamma is computed. No, of course.
Yes, and even in mathematics, Samson, it's somewhere computed. In physics, they are called BPS invariants, and you know all these exactly.
Right, but then the question, his question has an answer.
No. He asked in general whether this factors or the product of factors can be understood as certain Stokes automorphism for the non-linear connection. It's a theoretical question.
I talked about it on Friday, Phil.
Yep.
Yeah, that's my daughter's birthday.
Okay, so then attend Tom's talk and let me proceed. All right, so what I spoke about this quantum tori and other business at 3D Calabi-Yau categories, but there is a version for two-dimensional Calabi-Yau categories, like the category of Higgs bundles, just no singularities at all. So then its homological dimension is 2, so the Euler form is symmetric, so skew symmetrizing gives us 0. So the quantum torus is commutative, and we get just ordinary generating series. Yeah. So D here separated because in what I will be talking about, D will be a degree, but gamma, it will have a different meaning depending on the device.
Excuse me, are you touching the wire of the microphone?
Okay. All right, maybe I do, but okay.
Hands up.
Maybe just my chin, I don't know. Anyway, for gamma, if there are no marked points, then the gamma is just a rank. But in parabolic case, we need to take care about the jumps of ranks of flags. And so then gamma will belong to a certain monoid, and here it is basically a rank, and these jumps of flags, one for each point of the support of the divisor. Now, the analogs of these categories C of V, which appeared in this 3D story, yeah, this C of V anyway, everywhere. In my case, it will be the category of Higgs bundles such that the underlying vector bundle has a Harder-Narasimhan spectrum, which means this slopes of all semistable quotients which belong to the given V. Okay.
Yeah. When D is non-trivial, how do you get your CY3 category?
I don't want to go to CY3. What I am saying that I can do whatever we did with 3D Calabi-Yau, I can do it for 2D Calabi-Yau.
Well, it's just because your Higgs bundles are not now controlled by omega X, but
let me say, so I am speaking about Motivic Hall algebras, not cohomological Hall algebras, which are another story. For cohomological Hall algebra, there is a dimensional reduction from 3 to 2, which basically means that you take your Calabi-Yau surface, like the cotangent bundle, and multiply by a line. This is your 3 Calabi-Yau. But for Motivic, I don't do this. Right? So I'm just saying that I can repeat whatever, all whatever we did for 3, I can do it for 2. And we wrote some paper with my graduate student, I believe, GRN.
you can do it for any category, right? You don't need any Calabi-Yau.
No, I need quantum homomorphism and the quantum torus.
And you're saying this still exists in this?
Yeah. But in 2D case, it will be commutative. So that's the point. And so my no, I don't know.
Maybe it's, the zone is bad for the sound.
So
Sorry.
okay. Me too. All right. And now start the technical part. So we will work with epsilon connections, as I said, which mean that we will combine Higgs bundles and bundles with connections and parabolic star. It will be for epsilon connections. Now, in order to define singularities, first we define the space of normal forms. So we will have matrices, like in local coordinates, with entries which are differential forms, which might have poles of degree up to a fixed degree, multiplicity of the divisor. Yeah, so then it's useful to have this kind of, to define this space of all possible full normal forms. And actually, technically, in our paper, we need a relative version when we have two divisors. And the idea is that the big divisor controls poles of our, for example, of the Higgs bundle, of the connection, but we have a smaller divisor where we can put a parabolic structure. So it's kind of, and then we change the smaller divisor, and there is kind of induction which leaves in the end only this space. So, but anyway, this is a definition of formal normal forms, and now it's a bit dense stack, but it's a definition of the stack which we are dealing with. What we have here? Well, epsilon is just an element of our field. Well, x, we can probably skip x because we do not consider any change of x. It's another interesting question. There is an additional possibility to move x along the moduli space of curves. We fix x. Well, d is a effective divisor, and zeta is basically the eigenvalues for the Higgs field. So we fix at each point, we fix a level d parabolic structure, so like flags of free modules, as I said before, or truncated local rings. So it is required that, of course, these flags are compatible with epsilon connections, and so that's basically the last bullet is a compatibility property that, for example, if we consider in the local trivialization of a vector bundle, so this is just an epsilon connection, and this is a block matrix which with the block size corresponding to associated graded with respect to my flag, and the polar part of the diagonal is fixed. It's certain full normal form. It's certain, if you'd like, negative Laurent polynomial, or if you would like, you can consider negative Puiseux, but then you have to go to the universe, to the cover, finite cover. And the blocks below the diagonal have no poles, which means that modulo non-singular, our singular part is upper triangular. So that's a definition of the stack. But of course, it's what like everybody can imagine.
So in the hypercalar business, it's important to have like the real weights as well. So it's if you're
you will see later. It's not important. You can work with a slope stability and avoid hypercalar. So we are the arbitrary field of characteristic over complex numbers. It's the same.
Sure, but the question is to work out whether the spaces you're looking at are isomorphic to the ones which you
over complex numbers, yes, but probably we should use
without the real parabolic weight.
You will see them later. So this is a stack of everything. It's not semistables. It's just stack. Just imagine you consider bundles with. It's still a stack. You consider
not just about stability. Loads of algebraic people have not understood that the weights are not just about stability. But you need it for the moduli problem.
We don't need. No. Okay. So that's the definition of the stack. This is a notation for it. For epsilon, which is not equal to 0, actually each of these is a stack of locally finite type, so it can be proven. So that's the decomposition which I already mentioned over the, if you'd like, of the Chern classes. So it's pair rank and collection of jumps of flags, and D is, I separated it as a degree. So then this is the corresponding Donaldson-Thomas series, and we want to compute it, or rather individual coefficients. This is the first thing. And again, this is just an ordinary theory series in commuting variables. Yeah, because the quantum torus is commutative. All right, and now a couple of properties and the answer. So first, introduce this notation, gamma, kind of a star product with zeta, with my eigenvalues. It's some element of my ground field. And basically, if you see how it looks like, you can think of this zeta like in the simplest possible example of an object. You consider just diagonal matrices, like connections with connection matrices which are diagonal, and these are negative Laurent polynomial staying in the diagonal. So then this is basically sort of a residue of the trace. That's a product. Now, the result that first these stacks, as I said, they are of finite type. They are not of finite type for Higgs, so you have to introduce stability in that case. But for epsilon not equal to 0, they are of finite type. And they are non-empty only if this condition is satisfied. We found it's kind of generalization of André-Weil theorem, which says that if you have a bundle with connection, your bundle must have a degree equal to 0. There is an upgrade to irregular parabolic case. All right. Good. Now, let's introduce the irregularity index. Remember that nx were the coefficient multiplicities of my divisor. And so if they all equal to 0, excuse me, if they all equal to 1, which means I deal with regular singular case, then the irregularity is equal to 0. So, but in general, it's some delta. Good. And now comes something which I don't have time to explain. It looks a little bit scary, except of the first. It's kind of a motivical function, if you like, of the curve. And what comes next, it's a generalization of a certain kernel. People sometimes speak about Hausel kernel, but it was simplified by different people, including Anton Milit. And that's the version which we consider. So this part, it's a generation function, which you see, it's 3 lines. This is something which is more or less understandable, and it depends on the motive of the Lefschetz motive and the irregularity index. But of course, these two pieces are not easy to understand. So this is some rewriting of what Hausel wrote in his paper with collaborators in their work on the Hodge polynomials of the character varieties. All right, but at least what is some people, at least experts in the theory of symmetric functions, can see from the second line that it can be rewritten in terms of the symmetric functions of the Weil numbers if you are a finite field, and you have you factorize your zeta function, yeah, which you cannot do it motivically. So then it's something at least which belongs to the theory of symmetric functions, as well as the last factor these are generalized, these are modified Macdonald polynomials, or rather Motivic version of the ring of Motivic functions. And these factors, they are responsible for parabolic structure. All right, so these are certain kernels. Let's call them Hausel kernels, or irregular version.
Left-hand side, I missed. Left-hand side in the formula.
This is a definition. The left-hand side, it's a definition. No, not at all, no. But this is something which depends on the curve and some symmetric functions. You see, this is a sum over all partitions. For each partition, I have a product over block or squares. This is arm length, this is length. So everything, kind of all the notions.
There is no like the statement that left-hand side is some kind of volume or some kind of.
No, eventually.
Eventually, I will use this to write. Yeah, exactly. Yeah, you're right.
There is no definition of left-hand side as some volume.
No. It's rather I think that the aim of Hausel and collaborators, Letelier and Rodriguez-Villegas, was to use this kind of standard symmetric functions to write down answers for Hodge polynomials or whatever, E polynomials for characterized. So that's
Question.
yeah.
For a modular structural group, you think the sum of the partitions is replaced by sum of the representations?
It might be. The thing is that
You can't all J simultaneously.
no. He asked for other groups, not for JLN. Yeah, for other groups, this technique doesn't work. I will say a few words at the very end.
Here, and it's fixed, or is it?
No. It's for all. It's a union of stacks over all n. It's like, representations of quiver. You take all dimension vectors. It's all right. So anyway, I cannot help anyone with understanding this formula, so you should write to Hausel and ask how he came. It's really incredible, and we just modified it. So then it makes sense in this universal Motivic ring, which I mentioned at the very beginning, which does not depend on curve, it depends on genus of curve.
So if you want to select a specific GLN, would you pick a coefficient or some?
I can speak about partitions. If I'm not in GLN, I should take a torus and hopefully.
That was only, is some of these variables is it a general function? It is sum over n of Motivic invariants for the.
But this is a generating function.
He's asking if you fix the rank.
If I wanted to fix n, would I pick the coefficient?
You will see the answer. No. I mean, the answer will given for fixed rank and degree. All right. So let me proceed. You will see and. All right, so these generating functions start with 1, so it's up to some factor. Well, I can take the logarithm, pletistic logarithm of it, all right? So, and this omega mod is a pletistic exponent of something. So, now comes the theorem. That if we take the logarithm, pletistic logarithm, then what I get is a generating series in two variables, W and Z, and also it depends on the motive of the Lefschetz motive, but in Z they are polynomials, and this is really important.
Z responsible for what?
Z responsible for degree. Well, for degree of vector bundle, no, n is a rank. All right. So what else? So I'm almost ready to formulate the answer.
Responsible for rank.
I think W. W in the power of gamma, and gamma is a pair rank. And this but in fact, sum of jumps of flank is equal to the rank. So then, all right. So two conditions. One which I mentioned at the very, very beginning of my talk, that we can get the answer only when the flags are full. unfortunately. So that's a condition that the jumps are either zero, so two consecutive elements of length coincide, or they jump by one dimension, or rank jump by one. It's called full. And non-resonant, it's a very natural condition that, you know, it's here, that if you take two eigenvalues, their difference does not lose the pole. So it has a pole of the same order as a degree of my divisor. Okay, and this is the theorem without stability. So we introduce certain quadratic expression which depends on the irregularity index. And then the Motivic class for the stack of epsilon connections with all these data fix and fix this, if you'd like, parabolic rank and the degree, it can be computed explicitly in terms of this Hausdale irregular version of the Hausdale generating function. And you see here we have to take z equal to 1. So this is why it's important that we deal with polynomials in z. A priori, if you do not prove it, it's just rational functions. And it takes some efforts to do it, which use another theory of us with Maximov admissible series, which we introduced in the paper on cohomological whole algebras. Later it was revisited by Milit, and we used some interesting things which he also...
The formula was infinite sum of powers of z, no? Or it was finite sum?
In the end it's finite. Yeah,
so how does it come out? It looks like it was infinite sum of...
It looks as infinite... No, but there are some other parameters exist. It should be a convergent series in the ring of Motivic functions.
It's convergent?
In the ring of Motivic functions. And the small parameter in this ring is inverse to the Lefschetz motive. So it's...
Yeah, could you remind what is gamma? For example, what is r dot dot?
Okay, R is a rank of the vector bundle, and this is a vector, integer vector of jumps of ranks. Like in the regular singular case, it just jumps of dimensions of vector spaces.
Is it this the same as 1 over h bar in the talk that the Kaplanov gave just?
It's not 1 over h bar. I would say rather h bar.
Rather h bar, okay.
All right. Well, I have only a couple of minutes, so Philip, it's especially if when we introduce a stability, so we can do it. It's a slope stability. The only problem is that when we consider in the irregular case a subbundle of a parabolic, it's not necessarily parabolic. It does not inherits a parabolic structure, but the fact is that if we impose an extra condition, then indeed when we have a subbundle, then we have an induced epsilon connection on the subbundle and on the quotient. So then everything works. So this is weights which you were asking for. These are real numbers. So this is this is star product of gamma and sigma, blah blah blah. This is a definition which, in the case of complex numbers, coincide with what you know. Well, it's a slope definition in the irregular case. And now we can speak about semi-stable epsilon connections with all these data fixed. So now these are stacks of finite types for every epsilon, including epsilon equal to 0, like Higgs bundle case. And this is the answer for the Motivic class of the semi-stable locus with a given parabolic weights. So as you see, it's very much similar to what we had for non-semi-stable locus, and of course it is obtained from wall crossing of factorization formulas, which I mentioned at the very beginning of my talk. All right, so I'm out of time, so just final remarks. David, the general reductive group G. So very little is known, but people are started to be interested in that story. There is a paper by Bezrukavnikov with collaborators. They did null parabolic structure P1 with 2 marked points, irregular, and so they connected, well, Higgs, the stack of Higgs bundles, to the fine Springer fiber. This is one story. Now, well, it takes more than just one slide. Will take more. Let me mention on the similar, because 1 and 5, they are somehow related. You know, my son Alex, he wrote his thesis on Deligne-Simpson problem, like find matrices in given conjugacy classes with a product equal to 1, which is the same as find a regular connection, regular singular connection with residues which are in this way. All right. So it turns out that we can write down explicit form, I mean, somehow explicit formulas for the moduli stacks, which means that if we can prove, which we cannot, because we are lazy, maybe, that those answers give us non-zero Motivic classes, then we know how to solve Deligne-Simpson problem. We wrote about something about that in our 2019 paper, but there was a quite recent, actually it's after this, G.V. Yun with one of his students considered irregular Deligne-Simpson, again, P1 with 2 marked points, same setup, arbitrary group G, and it turns out that the answer can be expressed in terms of representations of rational Cherednik algebra, just which orbits are reachable, are good. So then there are plenty of things related to this. Let me stop.
Thank you. Questions?
So is the case of P1 with 2 marked points not well known, because that gives rise to the quantum group? Having a look at a twisted case, but they don't recognize the basic fact that that's the space you quantize to get the quantum group. No. I mean, I understand what he says, that you can... And to give the geometric explanation of the Lustig, Soibelman, Kontsevich group Breda.
Yeah, I know. I read your paper.
That is somehow, you know, the motivation to look at these connections having poles with, you know, P1 with 2 poles.
Well, of course, those guys, they work over a kind of arbitrary field, and actually even finite field, so I believe that it might be a problem for you and even for me in that case, because I understand even to write down this R matrix monodromidator. Well, I cannot comment. I mean, Bezrukavnikov gave a talk at the end seminar, and G.V. Yun did as well. But
they were for Lustig, but they didn't point out the fact that the Lustig operators occur in this situation of a pole of order 2.
They speak about some braid group action. That's
Have you connected with the work of Tony on, you know, the Betty numbers of wild characters?
Yes, and in our paper we referred to you and to Tony with collaborators. Actually, we checked one of your conjectures from a paper with Emmanuel and Ron about the E polynomials in the irregular case, and indeed we confirmed that it follows. So it agrees with, at least at the level we have been able to check.
The Motivic picture is supposed to project to give you like the Betty numbers and the Hodge numbers and everything, or just part of that?
No. They give us. It's not character varieties. Okay. So yeah, but yeah, if we are interested in topology like Poincare polynomials or Betti numbers, yeah, it can be derived from
So
this.
it will give the Betti numbers and the Hodge numbers of the.
Not Hodge number. The Hodge structure is different for the Higgs and for the character varieties.
Other questions? Yeah.
Can you develop 4.3 about psychotherapy?
Sorry, what was the question?
Yeah, actually, it's about point 3. You see, I missed very important part of my talk, and let me do it now. And actually, I do have a video, but I don't have time to. I have a special video which I should. So that's the main thing. People should kind of celebrate this slide, but then you see it says 31 on 36 slides. And that comes, it comes answer. So the point is, actually, it's observation of Schiffman and Vassero. First, you consider, let's say, called Jordan quiver, like one vertex and one loop. You consider nilpotent, finite-dimensional nilpotent representations. You look for the whole algebra. All right, and so you can embed the moduli stack to the positive part of the affine Grassmannian, such that the whole algebra corresponds to the to the affine Hecke algebra, at least in the limit. Now, if you are, this is a zero. If you like, this is a nilpotent Higgs field of a point. If you raise the dimension by 1, consider Higgs over a curve, then there is a similar story on the next 5 slides, where you can embed it in the kind of affine Hecke, double affine Hecke algebra, if you like, for the double Grassmannian. And it's related to the work of Braverman, Kazhdan, and Patnaik. They did it for periodic numbers, but probably you can do it for any non-Archimedean field. And the thing is that characteristic function of the nilpotent orbit goes to the characteristic function of the orbit in the affine Grassmannian or in the double affine. And when you look carefully under this correspondence, applying usual geometric Satake, you will see whole Littlewood polynomials. And it is known that if you fix Jordan type of the loop and fix a type of the flag, which this nilpotent is preserved, the answer for the number of such things, it's whole Littlewood polynomial. Now for Kazhdan, Braverman, Kazhdan, and Patnaik, you will see McDonald polynomial. So it agrees with our paper. Yeah. So that's
okay. One last question from Davide, and then lunch.
So you had a local expression for the sum of the ranks.
That's related exactly to this.
Do you have it? Could there be a local expression for fixed rank?
Yes. We have a local expression for fixed rank. Absolutely.
But still a sum over something.
Over some partition. Well, in the nilpotent case, yeah, it's sum over partitions with some symmetric functions. I can show it.
Yeah. Okay, well, let's thank Jan again.